All right, so last time we started section 10.3, we're looking at calculus on parametric equations. And the one that we're going to be starting with today is this second derivative. So it was right here. This was the piece that we're going to need again for today. So just as a reminder, we get the second derivative notation coming from the chain rule involving our derivative. And so we have the derivative of t for dy dx divided by the derivative of x with respect to t. And we're going to take a look at problem number 5. All right, so our directions say that we're going to determine the open t intervals on which the curve is concave up or down. And the one that we're going to look at, number 5, is x equals 2t plus the natural log of t, and y equals 2t minus the natural log of t. And I probably should have copied it over here. I'll just write it up here at the top. I'll put it in red so it's a different color. Remember our d, make sure I don't get the details wrong on it. Pull it back up. d2y dx2 is d dt of dy dx over dx dt. Kind of running out of space, but that's what we're looking for. Okay. So the first thing we need to do is we need to find those individual derivatives for x and for y. So what is x prime here?
2 plus 1 over t.
Good, 2 plus 1 over t. And y prime?
2 minus 1 over t.
Right, 2 minus 1 over t. Okay, all good? So we should be able to use that to find dy dx. So what's dy dx? Didn't everybody talk at once? 2 minus 1 over t over 2 plus 1 over t. Good. All right, and complex fractions are never pretty to work with, so we'll eliminate the double fractions by multiplying by t over t, which will give us 2t minus 1 over 2t plus 1. Is that all right? Okay, so that's our first derivative. So our second derivative, we need to do d2y dx2. So we need the derivative of 2t minus 1 over 2t plus 1, which means I'm going to use a quotient rule, right? Quotient rule says I do the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator 2t plus 1 squared. And I'm going to divide that by dx dt. And dx dt was, or x prime, is 2t plus 1. That is dx dt. Well, that was my simplification of it. Sorry. I probably have that wrong even in my notes. It was this one actually before I did it. Simplified. Okay, is that all right? Okay, so it's kind of a mess, but we're going to clean the numerator up and try to eliminate the complex fractions just like we did the last time. We can do the times t. Actually, that wouldn't be a bad idea even at this moment to eliminate part of my complex fractions. That doesn't eliminate everything, but it at least gives me a single denominator on the bottom, so 2t plus 1. And on top, let's see, I have 4t plus 2 minus 4t plus 2. So I think that's 4. Is that okay? Do you guys want to see it? 2t plus 2t plus 2, and then plus, or minus, I didn't say that wrong, 4t plus 2 minus 4t plus 2, so 4. And then the denominator of this is 2t plus 1 squared, and I multiplied by t, so I'll put the t up on top of the 4 to eliminate the fraction before. I can consolidate those two denominators by multiplying by the reciprocal. So this is really just 4t over 2t plus 1 cubed. All right, is that okay? So if you'll remember, in order to find out where concavity potentially changes, we need to have the second derivative do what? There's one of two things it can do. It can be equal to 0 or, you know what the other one was? Yeah, undefined, right? So either the numerator is equal to 0 or the denominator is equal to 0. And those may not actually be places where it changes concavity, but if it changes concavity, it will have to do so at one of those points. So this will equal dy d2y dx2. We want to set it equal to 0 or undefined, or we'll call it does not exist. I'll put d and e. So it's going to equal 0 at t equal to 0, because that's going to make the numerator equal to 0, right? How about the denominator? Where will the denominator equal 0? Negative 1/2. So it equals 0 here. Hang on. And it equals does not exist down here. Okay, is that right? Okay. All right, so those are the two potential places where I might change concavity. There's different things you could do. You can use a sign chart. That's the way that I tend to think about it, is with a sign chart. So I look at the values that are in and around those values. So I have negative 1/2, and I have 0, and I pick values in between. And what I'm picking in between is I'm picking values that are in between, and where I'm testing it is in the second derivative. I'm trying to decide if the second derivative is positive or if it's negative at specific intervals. So you just pick a number. So we'll pick, say, like negative 1 here. This one's not super friendly because I do have to pick a fraction like negative 1/4. And then over here I can pick a positive 1. So negative 1 and positive 1 are pretty fine, but the negative 1/4 is not fabulous. But remember, you're plugging it into the second derivative, and you might as well plug it into the simplified version of the second derivative because it's the nicer one. So if I put in negative 1, the top is negative. If I put in negative 1, is the bottom negative or is it positive? I think it's negative. The denominator, that is. Negative 1 times 2 would be negative 2. Negative 2 plus my 1 would be negative 1 cube's negative. Is that okay? So I'd get a negative on top, I'd get a negative on bottom, which means overall I would have a positive second derivative at negative 1. Negative 1/4 is a bit messier. I really don't care about the signs, so the negative 1/4 on the top gives us a negative. What does a negative 1/4 on the bottom give us? A positive. So I've got negative, I have a positive. This one actually is negative. And then on the last one, if I put in the number 1, do I get positives or negatives? Yeah, that one's positives. So it does, in fact, change concavity, right? So this one would be concave up from negative infinity to negative 1/2. And then again from 0 to infinity. And it would be concave down between them, between negative 1/2 and 0. Remember, it doesn't make sense to talk about concavity at any endpoints, so these are always open intervals. It also specifically said open intervals in the directions of the question, but even if it hadn't, they would be open intervals. Any questions on that? All right. Oh, I forgot about that. This is what happens when you cover up your notes. There is a problem with this that we didn't look at from the very beginning. I'm sorry about that. We did everything right. This is what happens when you do lots of calculations in between. take a look at the domain of our original question. The t can't be 0, and it also can't be negative, right? Inputs into logs have to be greater than 0. That's what happens. These are greater than 0 by default. So over here, this is true if I were able to use them. So that's actually okay. That's all right. I wanted to be able to show you a sign chart anyway, so that worked out. But the t value is always greater than 0. So for ours, that's the domain itself. So for our problem itself, it is only concave up, and it's on the interval from 0 to infinity. So sorry. I got so excited to do a sign chart. Haven't done one in a while. We aren't there in my Calc 1 class just yet. All right. Now we're going to move on into some antiderivative stuff. So the first thing we're going to look at in terms of antiderivatives is a quantity called arc length. And you've seen arc length before. It shows up for the first time in chapter 4, I believe. But we're going to be looking at arc length now for parametric form. We'll say arc length in parametric form.
Is this still 10.3?
It is. Yeah. 10.3 is kind of long, and in fact 10.5 is even longer. So yeah. So there's some long sections here in chapter 10. So this is arc length, and it says the following. If a smooth curve C is given by x equals f of t and y equals g of t, such that C doesn't intersect itself on the interval AB, then the arc length of C over the interval is the following. So it's S equals the integral from A to B of the square root of the derivative of x squared plus the derivative of y squared. Oops, a little too far. dt. We're finding a length, right? And this is an application of a distance formula. Do you see it there? Where you're looking at the change or how something is affecting the x value and it's squared, affecting the y value, it's squared, and then we take a square root. Yeah, so that's what's actually going on behind the scenes of this one. And beautiful things tend to happen when we do this in parametric form. So let me give you an example so you can see how lovely things work out when we're working on these. So we're going to find the arc length. And our example is x equals sine t cosine t, and y equals sine squared t. And we're going to use the interval from 0 to pi halves. So that's the formula we're shooting for, right? That's what we want to use, this antiderivative formula. What does it say I need to do once I'm given x and y? Yeah, I need derivatives, right? And if you take a look at each one of these derivatives, they're not quite as simple as some of the other ones we've been doing. So I have sine t, cosine t. What do I have to do in order to find the derivative of that one? Yeah, it's a product rule. So we have x prime. So I'm going to leave the first one the same and take the derivative of the second. Derivative of cosine is negative sine. I'm going to move these over. And then plus, and I need the derivative of sine, which is cosine, times cosine. So this is negative sine squared t plus the cosine squared of t. All right, so that one is x. Let me shift this over even just a little bit more, and we'll do y now. So what's the derivative of y? Yeah, 2 sine t cosine t. Okay, are those okay? Both of them all right? Excellent. So the arc length formula that we have above says that we're going to square each of those individually, right? Square the x prime, square the y prime, and add them together. And we're going to do some work with them after that. So I'm going to move this to the next slide because I'm not going to have space to finish it over here. I should have just started it on the next slide, but I didn't. And we'll continue from here. Okay, so arc length, which is a lowercase s, by the way, we're going to use a capital S in a little while, but this is a lowercase s, is the integral. What are my limits of integration? 0 to pi over 2, because it's the integration limits on t over there, or the interval limits on t. And then we have the sine squared of t. It was negative, right? Negative sine squared of t plus cosine squared of t squared. And then plus 2 sine t cosine t squared dt. Is that all right? It's going to look worse before it looks better. So please remember that you cannot square each of those individually. When we square sine squared and cosine squared all added together the way that it is, we're having to actually multiply it by itself, and we get inner and outer terms. And so I've got my 0 to pi halves here again, and I will end up having the negative sine squared squared. So this is going to be sine to the fourth. And then I'm going to have a sine t times cosine t, and then double it because I've got one on the inside and one on the outside. So it's negative 2 sine t cosine sine squared t cosine squared t. There we go. And then I have cosine to the fourth t. And then at the end, I now have 4 sine squared t cosine squared t dt. Do you see any things that can combine together? Yeah, there's negative 2 of them in the first piece, and there's positive 4 of them in the second piece. So when I add them together, what do I get? Yeah, I get positive 2 now. So I'm trading in, this is sine squared t, the negative 2 for a positive 2. That's a power of 4, sorry. Sine squared t cosine squared t. And then plus cosine to the fourth t dt. Okay, it's about to be really not icky. Are you ready?
That's a perfect square.
It is a perfect square. And it shows up at a really nice time because it's really similar to what I already had. And we know how that factored because it was right there, right? So we recognize that it's almost the same as what I had. It's just that it's a positive instead of a negative. So I don't have negative sine t. I have positive. And so as I'm factoring this, and it factors perfectly as you've noticed, this is the sine squared of t plus the cosine squared of t. And it's squared, and then I've got the square root of it. So when we square and we square root, they cancel. I told you it's going to be nice, right? So that's really good. I think I have too many parentheses there accidentally. Sorry about that. We'll cut that one out. And so, yes, and sine squared plus cosine squared also happens to be 1, which is just, even better. It's like icing on the cake. So I've got the integral from 0 to pi halves, literally of 1 dt. And the antiderivative of 1 is? T, because I'm working with t. And I'm evaluating from pi halves to 0. And if I evaluate those, I end up getting pi halves. So the length of this curve is pi halves between 0 and pi over 2.
Radians or degrees?
Radians. We're going to be working always in radians when we're in calculus. Yes. All right. Everybody good? Okay. So this one was the length of a curve, right? So we're finding the arc length. Do you remember this topic that you did in Calc 2 called solids of revolution? Oh, do you remember that one? What happened?
Complexity.
Yeah, like you were rotating things around different axes and they were creating these objects and you had things called disks and washers and shells. You remember all that? Okay. Well, we're doing something slightly different than that. Those are called solids of revolution. In that section as well, you learned about something called surfaces of revolution. So solids of revolution found volume, right? And the volume of the objects was a complicated item. It was. But when you found the surface area of those objects, it's far easier than finding the solids themselves. So we're actually looking at the surface area of these revolutions. So we're going to find the area of a surface of revolution in parametric form next. So this is theorem, 10.9. And this is area of a surface of revolution. And it says the following. If a smooth curve smooth curve C, given by x equals f of t and y equals g of t, does not cross itself, on an interval AB, then the area, and now we've got a capital S, of the surface of revolution formed by revolving C around the, I'm going to leave a blank here, blank axis, is one of two formulas. One, S equals 2 pi times the integral from a to b of g of t times the square root of x prime of t squared plus y prime of t squared. So that should look familiar. We just did that part of it, dt. Or, number 2, s equals 2 pi times the integral from a to b of f of t square root of x prime of t squared plus y prime of t squared dt. And the difference here, of course, is this piece, right? The g of t or the f of t. G of t is my equation for y, and f of t is my equation for x. So if I've got the equation for y in there, this is around the x-axis. And if the equation is in there for x, then it's around the y-axis. And that's what goes inside this blank right here. It's which axis I'm going to be working with. In each of these cases, the g of t or the x of t, g of t or f of t are both positive. So in the first one, g of t is greater than or equal to 0. On the second one, f of t is greater than or equal to 0 in order for this to work the way we're working with it. Okay, so we're going to do one last example, but we're going to rotate it around on both axes so that we have a chance to see how it looks a little bit different. The complication is very minimal. I mean, like the difference between the two is very minimal, so just doing both of them makes the most sense instead of creating a different example. So here is the example we're going to look at. We're going to find the area of the surface generated by revolving around the axis. Both the surface and the axis will be given in the problem itself. So we're on number 7. The first one, the surface is x equal t. Y equals 4 minus 2t. And we're working between, for t going from 0 to 2. And for part A, the one we're on right now, we're going to work with the x-axis. Okay, so I'll change color just so that it's differentiable, easily seen. What is my x prime? 1. And what is y prime? -2. All right, everybody good with that? This is a really simple derivative one. And we're going to be looking at the surface. The area of the surface is 2 pi times the integral from 0 to 2. And since I'm working on the x-axis, I use the equation for y. So this is 4 minus 2t, and it's in front of the square root. And then I have the square root of each of those derivatives I found, which happen to be constants, squared. So I have x squared, which would be 1 squared, and then I have -2 squared, like that. dt at the end, I'm almost out of space. All right, so that's square root of 5. Yeah, you guys are already finding it, no problem. So I've got the integral from 0 to 2 of 4 minus 2t square root of 5 dt. Square root of 5 is just a constant, so it could come out in front with a 2 if you want it to, right? It wouldn't hurt anything if it did. So I could write 2 square root of 5 pi if you wish. And then I need the antiderivative of 4 minus 2t. So what antiderivative of 4 is 4t, and the antiderivative of 2t is t squared. And I'm evaluating at 2 down to 0. Of course, evaluating at 0 gives me 0 because it's a polynomial. There's a t in each of the terms, so it's 0. So I really only have to evaluate at 2. So this is 2 square root 5 times pi. So if I put a 2 in, I have 8 minus 4. Right? So the grand whopping total here is what? Yeah, this piece is 4, and I'm multiplying it by the 2 square root 5 pi, so 8 square root 5 pi. So that's the first one. It's almost the same thing to do the other one. It's just this piece right here, I'll highlight it in blue, that will change, right? Instead of it saying 4 minus 2t, it's going to say just t, because that's the other variable. So let me shrink this so I have space on the same screen. So this was the x-axis one, and now we're going to do y-axis. So part B is y-axis. And again, most of it's the same. I have s equals 2 pi, interval from 0 to 2, and now I have t. It's the same square root process, so it's square root of 5 dt. So I have 2 square root 5 pi in front. And then what's the antiderivative of t? T squared over 2. And I'm going to evaluate it from 2 down to 0. And you can plug the 2 in if you wish, but you also could notice that the 2 here and the 2 here cancel if you wish. That would be fine. So I'll cancel mine, and now I have square root of 5 pi. And then I'm evaluating 2 squared. So I end up with 4 square root 5 pi. Okay. Not as bad as solids of revolution at all, right? Surfaces are much easier.